Professor Ilyashenko from Cornell University and Moscow State University.
Thank you very much. Allow me to try not to use any microphone. Am I heard? Is the microphone needed? Sorry? Okay.
Нужно остановить...
Is it better in this way?
No, because it's they will stop the conditional air now.
Does it work now?
Yes, it does.
Okay. Well, thanks.
They will stop the conditional air and
Thanks to the organizers for inviting me. It is a great pleasure for me to be here. Allow me some personal reminders. More than 30 years ago, Arnold and myself got a letter from 3 Mexican mathematicians with a suggestion to collaborate. The letter was signed by Pepe Seade, Javier Gomez Mont, and Alberto Verkhovsky. And soon after then, a long collaboration started. It covered more than a half of professional life and was a happy and various. In particular, Laura Ortiz and Ernesto Rosales came to Moscow and got their PhDs with Arnold and myself, respectively. So, best greetings to Pepe. Since then, I came many times to Mexico. Mexico became one of my favorite countries, and it is my great pleasure to be here again. A few words about the title. Rotation number is related to diffeomorphisms of a circle. It is an average rotation angle of a diffeomorphism which preserves the orientation. We will deal with only such diffeomorphisms. And moduli of elliptic curves are defined in the following way. An elliptic curve is a Riemann surface which is diffeomorphic to real two torus. This surface, by the uniformization theorem, may be represented as a factor of a complex plane C by the action of a lattice. And this lattice may be generated by 2 vectors. One of them may be taken standard from 0 to 1, and another one is variable, and it is the modulus of the elliptic curve. So, first of all, in order to give you an idea of what problem will be considered, I give you a model setting. We consider a circle as a factor of the real line by the action of integers, and we consider a shift which is also called a rotation. It is TA here, and we iterate it. A itself is the rotation number in this case. Another object occurs when we take A in the upper half plane. Again, we have a translation, but now the image of S1 is in the upper half plane. The picture is the following. We have a parallelogram. This is the image of S1. and we glue together the corresponding points on the sides. We factorize by z, and we factorize by the action of the translation TA. Then, after such a gluing up, we get an elliptic curve, and it is already uniformized. It is already obtained from a parallelogram by this gluing up. This is exactly the factor space of the line C over the action of a lattice. We get thus the elliptic curve with the modulus A. And we have the following trivial relation. When A tends to alpha real, then the modulus of TA tends to this alpha, and alpha is the rotation number of T alpha. So the question, the problem is, the goal is, make all this nonlinear. I will repeat the nonlinear setting 2 times, following the advice by Javier, who taught us that la repeticia is as la madre de el ciencia. Повторение мать учения. The first setting is when we consider the circle as a factor space of R over Z, and we consider a family of maps. Lambda is a parameter, and a family is, in a sense, monotonic. This means that the derivative of f in lambda is positive. We consider not only real lambdas, but complex one as well. In a general setting, the imaginary part is bounded by some positive constant. In what follows, it will be unbounded. Once again, we make the same construction. When lambda is in R, we have a function on lambda, which is rotation number of f lambda. When lambda is in H, in the open part of the upper half plane, then we have an elliptic curve T lambda, which is constructed in the following way. Again, we have the same parallelogram, but now gluing ups are along the points which differ by 1, and other 2 sides are glued together. We identified a point in the lower side and its image under f lambda. So this is a nonlinear construction. Yet we get an elliptic curve again, and this is a schematic picture. You may think about this elliptic curve as already uniformized. The uniformization theorem claims that there exists another complex number, modulus of the elliptic curve, such that exactly this elliptic curve may be obtained by gluing together the corresponding points on the sides of the parallelogram as it was shown in the previous picture. So instead of variable gluing, we have a constant gluing. And this constant is the modulus of the elliptic curve. So this elliptic curve is shown as uniformized, and these cycles on the elliptic curve are shown as curves and not now regular circles. this elliptic curve, as I said, is again biholomorphically equivalent to a factor of C over a lattice, and mu is a number in the upper half plane, and it is called the modulus of this elliptic curve. And the question may be asked, up to what extent the following limit relation is correct. The limit of the modulus of the elliptic curve as the parameter tends to a real value equals to the rotation number of the corresponding diffeomorphism of a surface. So this is a first setting of the problem. I will try to be understandable up to the very end, and therefore I will make some stops and ask people whether there are questions. Are there any questions right now? Yes?
Is it possible to calculate the moduli?
I will say about it at the end of the talk. In general, not. In general, this is not a calculational problem, finding the modulus. The second setting is similar to the first one. Yes, please.
I don't understand what's the relation between the gluing map and uniformization.
I will try to answer. I will try to answer. When you have a gluing map, you make a gluing of the sides of a parallelogram, and you get a surface homeomorphic to a two torus. It may be proved, I do not pretend to prove it now, that this is in fact a Riemann surface. Our diffeomorphism is always analytic, real analytic. We get a Riemann surface, and this is the first step. The second step is to use the general uniformization theorem to uniformize this surface and to say that this surface is biholomorphically equivalent to a factor space of C over a lattice. And the second vector of this lattice, the first vector is always 1, and the second vector is the modulus. And this is the relation. Is it okay? Well, I give the second setting. Consider S1 as a unit circle on the complex line. Let D be the open unit disk and D bar be the closed one. The rigid rotation of the circle is now multiplication by a number lambda with the modulus equal to 1. It is a rigid rotation. We can produce an elliptic curve in this model again. We take a multiplication by lambda. It brings S1 to a circle of a smaller radius if modulo lambda is smaller than 1. And we have this unit circle and this image of this unit circle. Once again, we glue up with respect to the source and target of this map. If this map is a rigid rotation, then we will get a uniformized elliptic curve. Look, when we glued up these two circles, we get again a torus, a surface homeomorphic to a torus. Again, it might be transformed, it has holomorphic structure, that is, this curve is a Riemann surface. It might be uniformized, and at the same time as in the previous setting, this curve is a factor space of C star C without zero, over multiplication by some complex number with modulus smaller than 1. And under uniformization, this circle becomes a curve on the torus, not necessarily the regular circle. So this picture also illustrates the case when the map is not a rigid rotation, but an arbitrary diffeomorphism of a circle. We will consider a family suggested by Arnold, which depends on a parameter in a very simple way. It is just fixed f multiplied by a parameter lambda from an open unit disk. Once again, we get an elliptic curve with a multiplicative modulus lambda, and this lambda is related to the previously defined modulus in this way, and it is a point in the unit disk. And the rotation number, this lambda is related to the previous rotation number in this way. It is a multiplicative rotation number. So, in what follows, we will speak only about multiplicative modulus of an elliptic curve and multiplicative rotation number, and about their relations. Here I make the second stop. Are people comfortable with that? This is the setting. Okay. So we consider the nonlinear version of the problem, and I repeat it. We have a real analytic diffeomorphism of a circle. We have this family, and the parameter is not only inside the unit disk, but on the boundary as well. When the parameter is on the boundary, we have a diffeomorphism of a circle. And we have a multiplicative rotation number of this diffeomorphism. When the parameter is inside the unit circle, then we have a previous construction and get a function mu of lambda multiplicative modulus of the corresponding rotation, of the corresponding elliptic curve. The problem is to study the limit behavior of this modulus when lambda tends to S1. So what is the limit of mu of lambda when lambda tends to the unit circle, and in particular, what is the relation of this modulus with the rotation number of the circle. So at last I am done with the setting. The results will be discussed, and first of all, let me stop and ask whether everybody is comfortable with this setting. Okay, now the results come. The main results belong to a younger participants of our Moscow group and to the quite mature French mathematician Risler, who is a student of Yokos. These results were obtained in his PhD thesis. So the names of the authors are Risler, Moldavskis, Buff, professor from Toulouse, Moldavskis, former Cornell graduate student, Goncharuk, present Higher School of Economy graduate student, and others. The first proposition, which may be easily proved and was first established by Risler, is that the function modulus of the elliptic curve is a holomorphic function. Therefore, in fact, as soon as the setting was pronounced, we get to the realm, to the theory of the boundary values of holomorphic functions in the unit disk. So now the main result about this function. First of all, the moduli function may be continuously extended to the boundary circle. So this is the interior of the unit circle, this is the boundary, and the modulus may be continuously extended. The image of this moduli map is a fractal set of a new kind. Rational points on the circle should not be literally understood. Rational points on the circle are roots of unity. But I will call them not roots of unity, but rational points for simplicity. At any rational point, there is a curve with a shape sort of a bubble, and this is a countable number of such bubbles. And the image of the boundary is the unit circle plus the union of all these bubbles. In what follows, I will give some terms from the theory of diffeomorphisms of a circle, and as soon as I conclude, I will explain these terms. Red are so-called hyperbolic arcs, and blue are so-called parabolic points. Hyperbolic arcs under the extended map mu come to the bubbles. Points on a circle which are in a sense irrational, this means that their argument divided over 2 pi is irrational. Those points for which the argument of the rotation number is irrational, this is an argument of the multiplicative rotation number. It is normalized. It is equal to the actual rotation number defined in the additive realization. If it is irrational, then the limit of our function is, of our multiplicative modulus, equals to the multiplicative rotation number. If the boundary map is so-called parabolic, then the same limit relation holds. So this is the result. And if I should give a short communication, and I will be short in time, then I will be forced to stop here and say this is the main result that I wanted to communicate to the audience. So once again, I stop here, and I am ready to answer questions about the result.
Are there decorations on the bubbles?
Are there decorations?
On the bubbles. It's a
Oh.
fractal set of the...
Well, I will speak at the end about the shape of the bubbles. Right now, these are just closed curves inside the unit circle with the endpoints in the rational point of the circle. I now recall the terms related to the theory of diffeomorphisms of a circle. A diffeomorphism of a circle is hyperbolic. I turn back to the additive realization. If the rotation number is rational and all periodic points z of the circle are hyperbolic, this means that we take the denominator of this irreducible fraction, take the corresponding iterate of f, then all the periodic points become the fixed points. And we require that the multiplier, the derivative at the fixed points, is different from 1. This is hyperbolicity. The requirement is that the rotation number is rational and all the periodic points are hyperbolic. A diffeomorphism is parabolic if the rotation number is rational and exists at least one so-called parabolic periodic point where the multiplier is 1. And we call hyperbolic arc the arc on a circle for which all the interior points correspond to a hyperbolic diffeomorphism and the end points correspond to parabolic diffeomorphisms. So these are the arcs that come to bubbles. Now the result is completely explained, and I switch to the ideas of the proof. This is sort of an exciting journey in the world of diffeomorphisms of a circle. I like to say that the world of diffeomorphisms of a circle is infinitely rich, and one may probably give a complete lecture course, a one-year lecture course about diffeomorphisms of a circle only. So, first of all, there are so-called Diophantine rotation numbers. These are the numbers that are not too well approximated by rationals. An irrational number is called Diophantine if for any reducible fraction p over q, the following inequality holds, and this c does not depend on the rational p over q. For the Diophantine rotation numbers, the limit of the modulus along the radius equals to the multiplicative rotation number. It was the Arnold's conjecture stated in 1978, and this conjecture was first proved by Rissler as a corollary of a great theory. His great theory was about linearizing of a circle diffeomorphisms, Bruneau condition, and so on. The theorem 1 was sort of a byproduct of his study. And the proof is based on a really great theory. Cornell graduate student Moldavskis gave a half-a-page proof of this theorem. This proof is based on the Hermann-Yocos linearization theorem and the theory of quasi-conformal maps. So, in this way, we are done with the Arnold's conjecture and with the Diophantine case. Now let us discuss what happens on the parabolic arcs, what happens in the hyperbolic case. In the hyperbolic case, there is a theorem due to Moldavskis and myself, which says that if the boundary diffeomorphism is hyperbolic, then the modulus of the corresponding elliptic curve will never approach to the unit circle. So when the parameter tends to the unit circle, r tends to 1, the modulus stays inside the lim sup is smaller than 1. Eight years later, the third-year undergraduate student Natalia Goncharuk proved that the moduli map may be analytically extended across the hyperbolic arcs. The proof is strongly based on the ideas of Javier Boeuf, and I will say a few words about my collaboration with Javier, about our collaboration with Javier Boeuf a little bit later. Let me explain why the moduli map may be extended analytically to parabolic arcs. The reason is the following. There are several ways of constructing the corresponding elliptic curve related to the parameter-dependent diffeomorphism. The construction that I illustrate below corresponds to the case when the rotation number is 0 and the diffeomorphism has fixed points, that is periodic orbits of period 1. For simplicity, I illustrate only the case when there are two fixed points, one attracting and one repelling. And I am back in the first setting, that is in the additive version of the representation of the unit circle. That is, it is a segment 0, 1 with the endpoints identified. Here is some information about the diffeomorphism. A is the attractor, R is the repeller. So A attracts everything from its neighborhood and R repels. If we take a small blue circle around A, then the image is inside. If we take a small green circle around R, then the image is outside. We can consider another curve which is a closed curve after this identification. It is a green curve. This part is attracted to A. This part is repelled from R, and therefore we get an image of a green curve, a brown one, which does not intersect the green one. And when we identify modulo Z, the points on the real line, we get an annulus. And when we identify the green and the brown curves along the map, we get an elliptic curve. And this elliptic curve corresponds to a value of the parameter not inside the unit circle, but on the unit circle. Therefore, we have a family of elliptic curves which is extended to the point of the unit circle. And in this way, we extend analytically the moduli function. It is easy to believe that when you perturb this construction and move the parameter even outside the unit circle, still the construction holds and the elliptic curve exists. This gives you an analytic extension of the moduli function across the boundary, across the parabolic arc. Let me describe for you what the previous construction implies with respect to the bubbles. This is an arc on the unit circle in the second setting. I get back to the second setting. This is the unit circle in the complex plane. And this is a parabolic arc. The interior points correspond to the parameter values for which the diffeomorphism is hyperbolic, and the endpoints correspond to the parabolic case. So this arc is mapped to this curve. And Buff and Goncharuk proved a theorem about a P over Q, about the size of a P over Q bubble. P over Q bubble has a vertex, is adjacent to a point which is a corresponding root of unity. The theorem claims that the whole bubble is included in a disk d rho 0. Rho 0 is a boundary point of the disk, not its center, whose radius is smaller than some constant depending on q squared, and this c does not depend on the rational number but on the diffeomorphism f only. So this is a theorem about size of a bubble. Let me now show you what happens at the endpoints. That is, let's now discuss the parabolic case. Suppose that we have something more complicated than I have shown in the previous picture. This large arc again corresponds to the parameter set on the unit circle for which the rotation number is rational, or the multiplicative rotation number is root of unity. One and the same for all the points of the arc. But it may happen, and it is explained how it may happen in this picture which I will comment soon. It may happen that not only the endpoints of the hyperbolic arc correspond to parabolic maps, but some interior points also correspond to parabolic maps. In this case, we have three hyperbolic arcs, and they produce three bubbles, like it is shown here. And some ends of the bubbles are called complex ends. Let me now explain you what does it mean. In this picture, the parameter axis is vertical, and once again it is the same arc as here, with the values alpha, alpha prime, beta prime, and beta the same. Here, I plot a part of a circle whose diffeomorphism is studied. And the green curve is a curve of fixed point of a map. Once again, I consider the case of rotation number 0. So, for a generic parameter value here, we have an arc of a circle here with two hyperbolic fixed points. When the parameter approaches beta, these two fixed points approach each other and collide here. This is a parabolic fixed point and a parabolic diffeomorphism. These two hyperbolic fixed points coexist for all the parameter values between alpha and beta and collide at alpha and at beta. We say that the corresponding bubble has a real end because its end is produced by the collision of the two hyperbolic fixed points seen in the real domain. Suppose that we have a similar pair of fixed points that correspond to the inner closed curve. These two hyperbolic fixed points coexist only for the parameters from the middle arc, and they collide at the points alpha prime and beta prime. Again, these ends are real ends of the bubble. But we have this bubble corresponding to this arc, and one end of the bubble is real, and the other end of the bubble is complex. It is produced by two fixed points that coexist in the complex domain and come to the real domain at this parameter value. So we have two kinds of ends of the bubble, real end and the complex end. And there is an interesting question: up to what extent the picture of the bubble which I have drawn is idealized? Is it correct that the bubble behaves well both at real ends and at complex ends? So the theorem 5, proved by Natalia Goncharuk when she was a third-year undergraduate student, claims that if alpha is the real end of the bubble, then the extended modulus of the corresponding elliptic curve tends to the rotation number, multiplicative rotation number, and multiplicative modulus, when the parameter tends to the end of the curve, and lambda is in the curve. This is quasi-conformal techniques used for this, for the proof of this theorem. Buff and Goncharuk together in the last year proved the same for complex ends. And this is a delicate statement which probably has several proofs. Up to now we have only one. So I delivered you how the limit values of the moduli function are studied when the parameter approaches to the point of a circle, which corresponds first to a Diophantine irrational rotation number, and second to rational rotation numbers, both in hyperbolic and parabolic cases. What is not yet described, what is left open? Left open is the case of the boundary values for which the rotation number is Liouvillean. That is, it is irrational but not Diophantine. Let us summarize what we already have. Consider a function on a circle which equals to the limit values of the moduli map if the map is hyperbolic, and to the rotation number if the map is non-hyperbolic. You see that this function is defined everywhere on the circle because we have an alternative hyperbolic, non-hyperbolic, and for both cases the function is well defined. What we proved about the relation of this function and the limit values of moduli maps. We know that the limit values of the moduli maps equal to this function provided that the corresponding diffeomorphism of a circle is either hyperbolic or its rotation number is Diophantine. There is a theorem by Tsuji. The set of such parameter values lambda has full measure on the unit circle. And there is a general theorem from complex analysis. Holomorphic function in the unit disk and a function on a circle which is continuous, and the limits of the first function equals to the second one for almost every radii in the disk, then f is in fact continuous. It's better to say that if you extend f by phi, f in d phi on S1, then this function is continuous in all the closed disks. The use of this theorem allows us to extend the result to the Liouville case if we prove that the function phi that we defined above is indeed continuous. It remains to prove that the function phi defined above is continuous at any point lambda in S1. First of all, consider the case when the rotation number is irrational. Then the danger of discontinuity comes from the bubbles. If the bubbles that accumulate to an irrational point are in a sense large, then we will have a discontinuity. But we have theorem 4 about the upper estimate of the size of the bubble. The larger is the denominator of a rational number, the smaller is the bubble. And therefore, when the rotation number is irrational, our function phi is continuous. When f lambda is hyperbolic, then we use the theorem about the holomorphic extension of the moduli function and get the continuity of the boundary function. The case when f lambda is parabolic is the most technical, but we use theorems 5 and 6, which are exactly statements about the continuity of the function phi of lambda, and this ends up the story. So this is the end of the main part of my talk, and my time is over. Well, I leave some small part non-delivered, and please.
Thank you very much. Are there any questions? Yes?
So, is Poincharenko inequality related to the cost inequality for the size of the bubbles of Mandelbrot?
You ask, repeat the last part of your question.
About the, for the size of the Mandelbrot bubbles of the Mandelbrot set.
Your cost inequality was used in the proof of the theorem about size of the bubbles.
What is the orientation of the bubbles?
Well,
And they are disposed in the same order as your picture.
About the bubbles, it is rather short. I give you a version of a visible monotonic family that is, as Carlos asked, is there a family where the moduli may be calculated? The answer is yes. You should start with a family of vector fields and suppose that these vector fields have a singular point. And consider the time one phase flow transformation of this vector field. You can write down the time function as you usually do for one-dimensional differential equations, and the observation is that this time function uniformizes the corresponding elliptic curve. Indeed, when you take from the source to the target, you spend exactly time 1, because this is a time 1 phase flow transformation. So you glue the values t and t plus 1, and when you identify these points, you glue the following values of t. These values differ by this integral, and therefore, instead of this integral, you want to have 1, and instead of this 1, you want to have the modulus. The modulus is 1 over the integral. And this is the case where you can explicitly calculate the moduli function and answer various questions about the family. This is not the Arnold's family. And allow me to show you just two open problems. Can the bubbles have this shape, self-intersections, mutual intersections? And what is the limit of the uniformizing function when, for the elliptic curve, when the parameter tends to the unit circle? So, thank you.
Any other questions?
Yes.
Yes.
Don't forget the last picture, please. Last picture.
Before we leave for the coffee break, Jean-Paul Vasselet would like to say a few words.
Masz